I'm excited because in this video, we are finally doing Stokes' theorem. So what's the idea of Stokes' theorem? Well, I want to begin with some surface. This is a two-dimensional surface embedded in 3 dimensions. And I'm specifically going to highlight the boundary of that surface because we're going to talk about the difference between the surface in general and its boundary a lot today. Then I'm going to imagine that the surface lives inside of some vector field. So I've just put it in this big, messy, swirling vector field. Okay, that's fine. It might help our visualization just to tell the computer to only draw the vectors that actually start from the surface, just to make it a bit cleaner. And I'm actually going to go even one step further at cleaning it up and now only draw the boundary curve and the vectors that start on the boundary curve. Now, the reason why I'm focusing just on the boundary here is that we know something about boundaries. We've studied this a lot. We have, for example, the property of the circulation along the boundary by this vector field f. And this was given by this particular line integral, the line integral of f dot dr. As I travel along this boundary, am I just circulating sort of with the vector field? That's what this is trying to capture. Now what I'm going to do is imagine that I'm at some point on the surface. And I have a normal vector that sticks away from that particular point, that is normal to the surface. This is going to be an oriented surface, so there's going to be 2 different choices of unit normals, one on either side, and I've just chosen one of them. But also at that point, from the vector field, there's a curl. And what the curl is going to do is going to create some tendency for there to be a rotation in the surface at that particular point. If I imagine, for example, my particle is not free to go anywhere, they have to go on the surface, but they're still influenced by the vector field, then they may rotate counterclockwise or clockwise, faster or slower, in this little region around the point that has normal vector this n. And indeed, I can go to any spot here, anywhere on the inside, and I can have a normal, and I'm going to have a little bit of swirling in the surface that's influenced by that vector field. Perhaps what is most important is if I go to a spot that is right on the boundary, like that one. So now it looks like the normal vector might go something along the lines of this. Or perhaps down here, and it would go more vertically. But at either spot, likewise, there would be a little bit of swirling going around. And here's the key point. Again, imagining I've got some sort of velocity field here. If I'm on the boundary and I want to ask the question, what is the circulation around the boundary? Well, the tendency to circulate along that boundary is going to be influenced by that curling at each point along the boundary. So the general formula, as we've seen, is that the curl at any point is given by del cross f. But then if I form del cross f and dot it with the normal vector at that point, that gives me the tendency to, how should I put it, curl within the surface. That is, the curl sort of subject to the constraint that we must remain on the surface. Before we get to Stokes' theorem, I want to go back a little bit and talk about Green's theorem, because in many ways Stokes' theorem is a generalization of Green's theorem. So the picture for Green's theorem is more or less the same scenario, it's just everything exists down on the plane. It's a 2-dimensional version of it. And because I'm going to upgrade to 3 dimensions, I just drew the 2 dimensions in the plane, but I included the 3rd axis because we want to add some stuff there in a little bit. And so when I look at this theorem, what it's really saying is on the left, we have that counterclockwise circulation as we were talking about, the tendency to circulate around the boundary. And what was remarkable about Green's theorem was that this was just equal to a double integral over the entire region, including all of that inside of something that we called the circulation density. What I'm going to do that's new about Green's theorem is just add a little bit new terminology. So you know how about the circulation density, this difference of these partials? Well, we saw in the previous video the curl of a vector field. And indeed, what I have here is just the kth component of curl. And so I'm going to replace that. I'm going to rewrite this as the curl, which was this del cross f, dotted with k hat, where k hat in my picture is sticking straight up out of the xy plane. So we have this upgrade on Green's theorem, which is just a terminology or a symbolic shift. We had this thing defined to be the curl, and I just recognized it as part of what was in Green's theorem before. And so I've just replaced it with our new symbols here, the del cross f, and then dotted with k hat. Another way to visualize what's going on a little bit better here, so I'll drop the 3-dimensional perspective and just look at this 2-dimensional, is all of these little spinners that I've drawn here, sort of regularly spaced out, give the tendency for this vector field to curl around at that particular point, at least curling in the xy plane. It depends on what the vector field is to know whether they're going to curl counterclockwise or clockwise, fast or slow. But the argument is going to be that in the interior, everything is just going to cancel out. And all that's left of all of this curling around is going to be the proportion, when you add it all up together, that's around the boundary. And the boundary adds up to the circulation. The argument for why it cancels is that if I have two adjacent little paths, then where they meet, in one path, it's the flow going up, and then in the adjacent path, it's the flow going right back down again. And so it exactly cancels in all of these interior portions. All right, so now let's go to Stokes' theorem. The first immediate difference is actually in my visualization. My surface is now a three-dimensional surface versus a two-dimensional surface. My vector field is a three-dimensional vector field, not a two-dimensional one. The left-hand side of Stokes' theorem is exactly the same. It's the circulation around that boundary curve. Yes, it's the circulation around a curve that lives in 3 dimensions as opposed to 2 dimensions, the way it was in Green's theorem, but it's the circulation around some curve. And then on the right-hand side, a couple things have changed. First of all, instead of being the curl dotted with k hat, it's the curl dotted with the normal vector. And that's because as you move to different places on your surface, your normal vectors are different things. It's not just k hat everywhere the way it was for Green's theorem. And the second thing that's changed is that instead of in Green's theorem, where I was taking a little area down in the xy plane, this is now a surface integral. It's an integral d sigma as opposed to dx dy or dA as we would have had before. But the sort of intuitive argument for why this is true is almost exactly the same. At any point in the interior of this surface, I have some curling that is measured by the curl of f dotted with n. So the curl that sort of lives inside of the surface, if you will. And then if you add up all of the tendencies to curl, everything along the inside cancels and just leaves with the curling along the boundary. And the curling around the boundary is what causes the circulation around this boundary curve. I do want to put up the conditions for Stokes' theorem. The field has to be nice, in this case continuous first partial derivatives of its components. And the surface also has to be nice. It needs to be a smooth surface, or at least it needs to be piecewise smooth. Like for example, a cube has those boundary edges and corners, but we still call the cube piecewise smooth. The real one I want to focus in though is the demand that it's an oriented surface. We'd seen previously an oriented surface meant the surface really had 2 different sides and you could choose a consistent or continuous choice of normals. We need to have a choice of normals to be able to compute the right-hand side of Stokes' theorem. And so Stokes' theorem really does depend on it being an oriented surface. So that is Stokes' theorem. Now, I definitely owe you a couple concrete examples. We're going to see that in the next video. We're going to see some remarkable corollaries of Stokes' theorem. But then I'm going to go to the divergence theorem because you might think, well, you just upgraded one of the 2 parts of Green's theorem. How do you upgrade the other part? And we'll be doing that when we get to the divergence theorem.